Well, let's take an extremely simple version. Let's take the Lagrangian, which is the other one, plus an offset. I call it 5 joules. Then obviously we get our Euler-Lagrange equations, which, because 5, when you take the derivative, just goes away, give us exactly the same Euler-Lagrange equations as before. So the very short answer is no, the Lagrangian is not unique. You can add any offset to it, just like you can with energy, and you still get the same behavior for everything that you see. So how far can we push this non-uniqueness? Remember, the reason that we use the Lagrangian is to compute the action. It's the action that's minimized, and the action is the integral from some initial time to some final time of the Lagrangian. And we don't have to get the action exactly the same, because all we need to do to see all the same behavior is we need that the paths that minimize this integral have to stay the same, which means we can construct a new action which is just equal to the old action plus some extra terms. And provided the extra terms don't affect the paths in the middle, then we're not going to get any change in our observable behavior. And we can make that happen by adding a function which depends on possibly all the coordinates, but only at the initial time and the final time. Because the paths that minimize going from a particular set of coordinates at the initial time and a particular set of coordinates at the final time are not changed by this, because these are at the edge like that. And so this will definitely give exactly the same behavior. And of course, if we write this as the integral, and we say, hey, that's just an integral of the derivative, then what we have here is that this is the integral from t1 to t2 of the Lagrangian plus the total derivative of m. And m is a function of my coordinates. So we can add to our Lagrangian any total derivative. If we look at how that expands out, m can depend on the coordinates only, and possibly time explicitly. There we go. So if we add terms like this to our Lagrangian, these can be quite non-trivial. They can be constructed from any function of our coordinates that we like. Then we'll get exactly the same paths that minimize our action, and so therefore we'll get exactly the same physics. This is called a gauge transformation of our Lagrangian. That's the general version. Let's go over that with a specific example. Let's look at the harmonic oscillator, one of the physicists' favorites. It's just kinetic energy minus potential energy. The kinetic energy in one dimension is just half mx dot squared, and the potential energy is just quadratic in x. So we've got an omega squared x squared. And our gauge has to have one less frequency because it's got a ddt compared to the Lagrangian. It's got to be a function of x and t. We'll just make it quadratic in x. So we'll make it, say, a half. We'll lose one frequency, so just half m omega. Alright, now if we calculate the new Lagrangian, the transformed Lagrangian, we're going to get the old one, plus these extra terms. This dot product is only one coordinate, so there's just one of them. And there's no explicit time dependence, so that's easy. So this all comes out to that, which clearly looks like, which is definitely different to our original Lagrangian. And you can go ahead and verify that this new Lagrangian, in fact, gives exactly the same Euler-Lagrange equations as the harmonic oscillator.